The fastest spacecraft humanity has ever built took nearly a decade to reach Pluto. That probe is still traveling deeper into the Kuiper Belt right now, and it will never return. If we sent humans on that same journey, they wouldn't survive the trip. Not because of a technical flaw we could fix, or an engineering problem we could solve, but because of something far more fundamental: the human body itself. The Kuiper Belt starts roughly 2.8 billion miles from Earth. To visualize that distance, imagine you could drive a car at highway speed directly into space. You'd reach the Moon in about 5 months. Mars would take around 3 years. But the Kuiper Belt, you'd be driving for over 5,000 years before arriving at its inner edge. And that's just the beginning of the problem. New Horizons launched from Cape Canaveral on January 19, 2006, screaming away from Earth at 36,400 miles per hour, the fastest launch velocity ever achieved. Engineers stripped away everything they could to maximize speed. No sample return capability, no landing gear, just instruments and the bare minimum to keep them functioning. Even at that blistering pace, Pluto's flyby didn't happen until July 14, 2015. 9.5 years for a machine designed to do nothing but travel as fast as physically possible. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Here's what makes that timeline catastrophic for human missions. New Horizons used every gravitational assist available, threading past Jupiter to steal momentum from the solar system's largest planet. A human crew couldn't replicate that trajectory. They'd need slower, more conservative paths to ensure safety. They'd require fuel for course corrections. Most critically, they'd need fuel to slow down upon arrival, something New Horizons never had to consider because it was designed for a flyby, not a visit. When you account for all those constraints, a human mission to the Kuiper Belt transforms from a 9-year sprint into a multi-decade marathon. Current estimates suggest 20 to 40 years minimum, assuming propulsion technology that doesn't exist yet. That time frame alone should raise alarm bells. But the real nightmare begins when you consider what happens to a human body over those decades. Your bones are constantly rebuilding themselves on Earth. Gravity provides the stress signals that tell your skeletal system to maintain its density. Remove that gravitational load, and your body responds logically. It stops wasting resources on bone mass you apparently don't need. Astronauts on the International Space Station lose between 1 and 1.5% of bone mineral density every month. After just 2 years in space, an astronaut could experience bone loss, equivalent to what an elderly person develops over decades of aging on Earth. Now multiply that deterioration by 10. By 20, ISS astronauts return to Earth after 6 months and require extensive rehabilitation just to walk normally again. Some never fully recover their bone density. What happens after 20 years of continuous microgravity? The math becomes grim quickly. After a decade, you're looking at potential bone density loss exceeding 30%. Your skeleton becomes fragile as glass. Your vertebrae compress. Calcium leaches into your bloodstream and forms kidney stones. And unlike ISS astronauts, you can't come home for rehabilitation. There is no home. Just the endless black between you and a destination that's still years away. Exercise helps, but only partially. Astronauts on the ISS spend 2 to 3 hours daily fighting their body's deterioration on specialized equipment. That's 2 to 3 hours every single day for decades, in a spacecraft where space is premium and every kilogram of equipment had to be justified before launch. The treadmills wear out, the resistance bands degrade. Replacement parts? There aren't any. You brought what you brought, and when it breaks, it stays broken. But bone loss is just the opening act. Your muscles atrophy faster than your bones deteriorate. Without gravity constantly pulling you down, your heart doesn't need to work as hard to pump blood. It weakens. Your cardiovascular system evolved over millions of years to operate in Earth's gravitational field, begins to fundamentally reshape itself for an environment it was never designed to inhabit. Studies have found that extended spaceflight may cause premature aging of the brain, damage to gastrointestinal tissues, and changes to the immune system so severe that dormant viruses reactivate inside astronauts' bodies. Then there's your vision. In microgravity, fluid shifts upward. On Earth, gravity pulls bodily fluids down toward your feet. In space, those fluids redistribute toward your head and chest. This increased cranial pressure can flatten the back of your eyeballs, changing their shape. Some astronauts have returned from 6-month missions with permanent vision changes. They went up with 20/20 vision and came back needing glasses they'll wear for the rest of their lives. NASA calls it Spaceflight-Associated Neuro-Ocular Syndrome. After 20 years, you might not be able to see the instruments you need to pilot the spacecraft home. Radiation makes everything worse. Earth's magnetic field shields us from the cosmic radiation that permeates space. On the ISS, astronauts still receive some protection because they're in low Earth orbit, close enough that the planet's magnetosphere provides partial shielding. Beyond that protective bubble, you're exposed to the full force of galactic cosmic rays, high-energy particles that slice through spacecraft hulls like they're not even there. NASA's career radiation limit for astronauts is 600 millisieverts. That's the maximum cumulative dose designed to keep cancer risk below 3%. A round trip to Mars, lasting around 18 months, would expose astronauts to radiation doses approaching or exceeding that entire career limit. The Kuiper Belt mission would last decades. You'd accumulate doses measured in sieverts, not millisieverts, orders of magnitude beyond anything considered remotely safe. Cosmic rays don't just increase cancer risk. They damage the cardiovascular system. They harm the central nervous system. They cause chromosomal aberrations in lymphocytes, the cells central to immune function. Your immune system would steadily collapse while you're trapped in a tin can with 5 other people, breathing recycled air, drinking recycled water. When someone gets sick, everyone gets sick. And there's no hospital, no emergency room, just whatever medical supplies you brought, operated by whoever among the crew has the most medical training, which probably amounts to advanced first aid. Shielding could theoretically help, but here's the physics problem. The most dangerous particles are also the hardest to stop. You'd need meters of material, water, polyethylene, or other hydrogen-rich substances to provide meaningful protection. Every centimeter of shielding adds tons of mass. Every ton of mass requires more fuel to accelerate, more fuel to decelerate, larger engines, stronger structures to support those engines. The spacecraft grows exponentially with each improvement in radiation protection, and we haven't even addressed where all that fuel comes from or how you carry enough to last decades. Chemical rockets, which have powered every human spaceflight to date, are fundamentally inadequate. The energy density of chemical propellants creates a hard ceiling. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that additional fuel. The tyranny of the rocket equation makes a chemical-powered Kuiper Belt mission physically impossible with any amount of fuel you could realistically launch. Electric propulsion offers better efficiency, but produces thrust measured in fractions of a newton, roughly equivalent to the weight of a few sheets of paper. These systems can run for years, gradually building up speed, which works fine for robotic probes. But humans need radiation shielding. They need life support. They need food, water, and living space. The mass penalty transforms electric propulsion's advantage into a marginal improvement at best. Nuclear thermal propulsion remains theoretical for human missions. The concept is sound. Use a nuclear reactor to superheat propellant and expel it at velocities impossible for chemical rockets. The specific impulse doubles or triples compared to conventional engines. But no nuclear thermal rocket has ever flown with humans aboard. The engineering challenges are immense. The political obstacles might be even larger. And even if we solved both, you're still looking at decade-long transit times. The Parker Solar Probe holds the record as the fastest human-made object ever built, reaching speeds of 430,000 miles per hour during its closest approach to the Sun. That's fast enough to travel from New York to Tokyo in less than a minute. But the Parker Solar Probe achieved those speeds by diving toward the Sun and using Venus gravity assists, a trajectory completely incompatible with reaching the Kuiper Belt. When you're traveling away from the Sun into the outer solar system, you can't use the same tricks. Voyager 1 is currently moving away from the Sun at 38,600 miles per hour, and that's about as fast as we've managed to push something in the right direction. Even assuming some revolutionary propulsion breakthrough, the distance itself remains unchanged. 4 billion miles is 4 billion miles regardless of how you travel it. At best, with technology that exists only in concept papers, you might cut the journey time to 15 or 20 years one way. You're still asking human beings to spend 30 to 40 years of their lives traveling to a destination they'll barely glimpse before turning around for the journey home. Let's talk about what you're eating during those decades. A single astronaut requires approximately 5 kilograms of food, water, and oxygen daily. That breaks down to 0.84 kilograms of oxygen, 0.62 kilograms of food, and 3.54 kilograms of water. For a crew of 6 on a 30-year mission, you're looking at over 300 metric tons of consumables. For context, the entire International Space Station has a mass of about 420 metric tons, and it required more than 40 launches to assemble. You can't carry 30 years of supplies. The spacecraft would be impossibly massive, so you need closed-loop life support systems, technology that recycles everything with near-perfect efficiency. The ISS Environmental Control and Life Support System currently achieves about 98% water recovery. That sounds impressive until you calculate what a 2% loss rate means over 3 decades. You'd run out of water years before arrival, and that 98% figure comes with caveats. It requires replacement filters, stored oxygen reserves, and regular maintenance from ground support teams who can send up new parts every few months. In deep space, there is no resupply. When a filter clogs, you can't order a replacement. When a pump fails, You either fix it with what's on board, or everyone dies. The system has to be completely closed, running at essentially 100% efficiency for longer than any mechanical system has ever operated continuously. Every valve, every membrane, every seal must function perfectly for decades in an environment of temperature extremes, radiation exposure, and vacuum just beyond the hull. Current biological life support systems can't achieve that reliability. Growing food in space requires light, water, nutrients, and careful environmental control. Plants need specific wavelengths of light for photosynthesis. They need the right temperature, the right humidity, the right atmospheric composition. You need backup systems for your backup systems, because a single crop failure could mean starvation months or years before you could grow a replacement. And all of this requires power, enormous amounts of continuous power. Which brings us to the power generation problem. The Voyager spacecraft launched with radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity. Each RTG initially produced about 157 watts. That plutonium has a half-life of 87.7 years, and after 46 years in space, both Voyagers have lost significant power output. They're currently losing about 4 watts per year. Scientists have had to shut down instruments to conserve energy, choosing which systems stay alive and which go dark. A human mission needs orders of magnitude more power. Life support systems, heating, communications, artificial gravity if you're using rotating sections to combat bone loss, computers, medical equipment, food production. You'd need multiple RTGs just to match the Voyager's initial output, and their power would decline over the mission duration. Solar panels become useless beyond Mars. At the Kuiper Belt, sunlight is roughly 900 to 2500 times weaker than at Earth. You're essentially operating in permanent twilight. Nuclear fission reactors could theoretically provide more power, but they introduce staggering complexity. How do you cool a reactor in vacuum? How do you shield the crew from the radiation it produces while simultaneously shielding everyone from cosmic radiation? How do you ensure it operates flawlessly for decades without maintenance impossible to perform in deep space? No nuclear reactor has ever been designed for this application. We're not even close. The psychological dimension might be the most overlooked factor. NASA's data shows that even on the ISS, where astronauts can see Earth and communicate in real time with loved ones, significant percentages report symptoms of anxiety and depression. The numbers are stark. 22.8% of male astronauts and 85.2% of female astronauts showed anxiety symptoms. Depression affected 34.8% of males and 43.2% of females. These are 6-month missions with a home planet visible through the window. On a Kuiper Belt mission, Earth becomes an insignificant blue-green dot, then disappears entirely into the glare of the sun. Communication delays stretch from seconds to minutes to hours. By the time you're deep in the Kuiper Belt, a message home takes 4 to 7 hours to arrive, and the response takes just as long. You ask Mission Control a question in the morning and might receive an answer the next day. Real-time support becomes impossible. You're on your own in a way no human has ever been. Isolation studies on Earth have documented what happens during extended confinement: cognitive decline, attention deficits, interpersonal conflicts that escalate because there's nowhere to escape. The Antarctic research stations provide some data, but even there, Crews know rescue is theoretically possible, and their missions end after a year or two. The Kuiper Belt crew would face decades of confinement in a space smaller than most houses, with the same 5 people, eating recycled food, breathing recycled air, knowing that any critical failure means certain death, and there's no cavalry coming. The longest continuous human spaceflight record is 438 days, just over 14 months. That's the absolute limit of what we've proven humans can endure. And those cosmonauts return to Earth requiring extensive medical care and rehabilitation. Extending that duration to decades isn't just difficult. It enters completely uncharted territory where our understanding of human physiology and psychology breaks down entirely. Here's what we haven't discussed yet. You still have to come back. Every challenge I've described, you face it twice. The radiation exposure accumulates on both legs of the journey. The bone loss continues. The psychological strain compounds. The life support systems must function twice as long. And if anything goes catastrophically wrong on the return journey, you're even farther from any possibility of help than you were on the outbound leg. But there's something even more fundamental than the engineering challenges, the physiological deterioration, or the psychological toll. Something that makes a crewed Kuiper Belt mission impossible, regardless of how many technical problems we might solve. It's a constraint so absolute that no amount of money, willpower, or scientific breakthrough can overcome it. Human lifespan itself. Let's do the math. You're 28 when you launch. That's young for an astronaut, but this mission demands people at the beginning of their careers, not the end. The outbound journey takes 20 years with optimistic propulsion assumptions. You arrive at the Kuiper Belt at 48. You spend perhaps 2 years conducting research, exploring, documenting. You're 50 when you begin the return trip. Another 20 years. You land back on Earth at 70 years old. That's the absolute best case scenario, and it assumes everything works perfectly. Now consider what those 42 years actually mean. You left Earth as a young adult. You return as someone approaching the end of their natural lifespan. Your parents are likely dead. Your siblings are elderly. Any children you had are middle-aged adults you've never really known. The world has changed in ways you can barely comprehend from your limited communications. Technology has advanced. Culture has shifted. You're returning to a planet that's essentially foreign. But that's not the real problem. The real problem is that you probably don't make it back at all. Human life expectancy, even with the best medical care, tops out around 80 to 90 years for most people. Launch at 28, and you're banking on living to 70 in perfect health after 4 decades of conditions that actively destroy human physiology. Except, you won't be in perfect health. The radiation exposure alone reduces life expectancy. The bone loss, muscle atrophy, cardiovascular deconditioning, all of these accelerate aging. Studies on long-duration spaceflight show that cosmic radiation doesn't just increase cancer risk, it ages you prematurely. Your cells accumulate damage faster than they would on Earth. Your telomeres shorten more rapidly. Your organs wear out sooner. You're not just 70 years old chronologically when you return. Biologically, you might be 80 or 90. The mission duration isn't just long, it's approaching the entire span of a human life. What if something goes wrong 15 years into the outbound journey? You're not even halfway there yet. Do you turn around? That adds decades to the mission. Do you continue forward? You're committing to completing a mission that now might extend beyond your lifespan. There's no good answer because the fundamental constraint, human mortality, cannot be negotiated with. Some enthusiasts propose generational ships as the solution. Build a vessel large enough that people can live, reproduce, and die during the journey. The crew that departs Earth isn't the crew that arrives at the destination. Their children or grandchildren complete the mission. This concept immediately raises questions that have no satisfactory answers. How do you ethically justify condemning people to be born, live, and die in a metal tube? They never consented to this existence. They never had a choice. What happens when the second or third generation decides they don't want to continue the mission their grandparents started? The psychological implications are staggering. Earth becomes a myth, a story told by elders about a place no one alive has ever seen. The mission becomes an abstract concept rather than a shared goal. Maintaining social cohesion across generations in such confined circumstances would require social engineering on a scale we've never attempted. And you still need enough genetic diversity to avoid inbreeding. That means a starting population of hundreds, possibly thousands. The ship's mass increases exponentially. Life support requirements multiply. The engineering challenges don't just grow, they explode into impossibility. But let's return to the single-generation mission, because that's what most people envision when they think about space exploration. The cold arithmetic of human lifespan creates an unavoidable conclusion. You cannot complete a round trip to the Kuiper Belt within the productive years of a human career. Astronauts typically retire from active duty in their 50s or early 60s. They're done flying missions long before 70. The physical demands are too great, the health risks too severe. Yet a Kuiper Belt mission requires you to remain mission capable into your 7th decade. You need to operate complex equipment, make critical decisions, perform emergency repairs, conduct scientific research, all while your body and mind are deteriorating from age and the accumulated damage of the journey. You're asking people to spend their entire adult lives on a single mission. Every birthday, every holiday, every major life milestone occurs in the same cramped spacecraft with the same small group of people. You never attend a wedding unless it's between crew members. You never meet your grandchildren. You never walk on a beach, hike a mountain, or feel rain on your face. Your entire existence becomes the mission. The psychological literature on confined environments suggests this is unsustainable. Humans need variety, novelty, natural environments. We didn't evolve for decades in artificial habitats. The Antarctica research stations rotate crews specifically because they've learned that even in relatively comfortable conditions with beautiful scenery and the knowledge that rescue is possible, people deteriorate mentally after a year or two. Some argue that advances in life extension technology might solve this problem. If we can extend human lifespan to 150 years, a 40-year mission becomes feasible. But this is circular reasoning. We don't have life extension technology. We can't assume it will exist when we need it. And if it does exist, it will likely take decades to prove safe and effective. You can't launch a mission banking on medical breakthroughs that haven't happened yet. There's also a more subtle problem with the lifespan constraint. Training for a Kuiper Belt mission would take years. You need to master multiple disciplines: spacecraft operation, life support maintenance, medical procedures, scientific protocols, emergency response. The complexity far exceeds anything astronauts currently learn. If training takes 5 to 10 years, you're now looking at launching people in their early 20s. They haven't fully matured cognitively. Their risk assessment capabilities aren't fully developed. You're asking them to make a commitment that will consume their entire lives before they're really equipped to understand what they're committing to. And what happens if someone changes their mind? 5 years into the mission, a crew member decides they can't do this anymore. They want to go home. There's no going home. There's no early exit. You're locked in for the duration. The psychological toll of that realization that you're trapped could be devastating. The mission planners would need to screen for psychological resilience with unprecedented rigor. But how do you test someone's ability to handle 4 decades of confinement when the longest anyone has ever done is 14 months? You're extrapolating far beyond your data. You're guessing. Even if you select the most psychologically robust individuals on Earth, you're still asking them to do something no human has ever done. The uncertainty alone is crushing. You don't know if you'll make it. You don't know if the life support will hold out. You don't know if the radiation shielding is adequate. You don't know if your mind will remain intact. You're pioneering into unknown territory, where the cost of failure is your life and the lives of everyone with you. Let's examine another temporal constraint: mission obsolescence. Technology advances rapidly. The spacecraft you launch in 2030 will be obsolete by 2050. By the time you reach the Kuiper Belt in 2050, there might be newer, faster ships being built that could make the journey in half the time. Do you abort your mission because you're redundant? Do you continue knowing that everything you discover might be discovered more efficiently by a later mission? This has already happened with robotic missions. Voyager was overtaken by faster probes. New Horizons flew past Pluto after decades of travel, but newer missions with better instruments are already being planned. The timeline for human missions makes this problem far worse. You're committing resources and human lives to a 40-year endeavor that might be rendered pointless by technological advancement before you're halfway done. There's no elegant solution to the lifespan problem. You can't meaningfully extend human life with current technology. You can't reduce travel time to the Kuiper Belt without propulsion systems that don't exist. You can't make the mission shorter without sacrificing the science objectives that justify the mission in the first place. Some propose suspended animation or hibernation as the answer. Put the crew in stasis for most of the journey. Wake them only when needed. This appears in countless science fiction stories because it solves the problem narratively. But the biology is nowhere close to reality. We can't put humans in suspended animation. We can't even put them in a medically induced coma for more than a few weeks without serious complications. The longest anyone has been in a coma-like state and recovered fully is measured in months, not years. Decades of suspended animation exists only in fiction. The metabolic processes required to maintain life can't simply be paused. Cells continue functioning or they die. There's no intermediate state that preserves complex organisms for years. Even if we could induce hibernation, you still need monitoring systems, medical equipment, power supplies, all of which must function flawlessly for decades. One failure and the crew dies in their sleep. The risk doesn't disappear. It just shifts to different systems. The lifespan constraint intersects with every other challenge we've discussed. Radiation exposure accumulates over time. More time means more radiation. Bone loss happens monthly. More months mean more loss. Psychological stress compounds. More years mean more stress. You can't solve any of these problems without addressing time, and you can't address time without faster propulsion or longer human lifespans. Neither is coming soon enough to matter. What this means practically is that anyone who volunteers for a Kuiper Belt mission is volunteering to never have a normal life again. They're sacrificing everything: family, career, experiences, freedom, for a single goal. The dedication required is almost incomprehensible. And unlike shorter missions where astronauts return as heroes to resume their lives, Kuiper Belt explorers would return as elderly individuals to a world that's moved on without them, if they return at all. The tragedy is that we can send robots. We are sending robots. New Horizons proved we can explore the Kuiper Belt remotely. The spacecraft is still functioning after nearly 20 years. It's collecting data, sending images, expanding our understanding of this distant region. And it didn't require life support, food, water, or psychological counseling. Every argument for sending humans to the Kuiper Belt runs into the same wall: time. Human lifespans are finite, and the journey exceeds what we can reasonably survive. You can't engineer around mortality. You can't design a spacecraft that keeps people alive longer than human biology allows. You can't train someone to withstand 4 decades of deterioration. The math is merciless. The numbers don't work. And unlike engineering challenges where clever solutions might emerge, the biological constraint of human lifespan is absolute. The psychological dimension deserves its own examination, because even if you solved every physical challenge, radiation, bone loss, life support, the human mind remains the weakest link. Astronauts on the International Space Station experience depression and anxiety at rates that should alarm anyone planning longer missions. NASA's own data shows 85.2% of female astronauts exhibit anxiety symptoms. These are highly trained, psychologically screened individuals on missions lasting months, not decades. They can see Earth from their windows. They video call their families daily. They know rescue is possible if something goes catastrophically wrong. Strip all that away. That's a Kuiper Belt mission. Earth becomes a dot indistinguishable from stars within weeks of departure. Communication delays stretch from seconds to minutes to hours. By the time you're deep in the journey, sending a message home and receiving a response takes most of a day. You can't have a conversation. You can't get real-time support. You're essentially sending letters into a void and waiting for letters back. The Mars mission planners worry about 44-minute round-trip communication delays. That's nothing. The Kuiper Belt sits 30 to 50 times farther from the Sun than Earth. Do the math. 4 to 7 hours one way at minimum. Want to talk to mission control about an emergency? Send your message, then wait up to 14 hours for advice. By then, you're either alive because you solved it yourself, or dead because you couldn't. This communication isolation compounds with physical isolation in ways we don't fully understand. The longest anyone has experienced this level of separation from Earth is never, not even close. Astronauts on the ISS are closer to Earth than many cities are to each other. They orbit our planet every 90 minutes. They're still connected to humanity in a fundamental way. A Kuiper Belt crew loses that connection permanently. No rescue mission is coming. No abort to Earth option exists. You're committed from the moment of launch to seeing the mission through or dying in the attempt. That psychological weight is incomprehensible to anyone who hasn't experienced it. Research on isolated environments, Antarctic stations, submarines, remote research facilities, gives us clues but no real answers. These environments are harsh but temporary. Researchers know they're leaving eventually. They can email freely. They can be evacuated in emergencies. The psychological profile of someone who volunteers for a year in Antarctica bears little resemblance to someone who'd need to survive 40 years in a metal tube hurtling through space. The Soviet cosmonaut Valentin Lebedev struggled with depression after only 7 months aboard a space station. 7 months. A Kuiper Belt mission would last 50 times longer minimum. How do you screen for that? What psychological test identifies someone capable of handling something no human has ever handled? You can't simulate it accurately on Earth. Every simulation has an escape hatch. Participants know they can quit. They know it's not real. The moment you remove that safety net, the psychological experience transforms completely. It's the difference between practicing a tightrope walk with a net below and walking that same rope over a canyon. The physical act is identical. The mental experience is incomparable. Confinement affects humans in ways that accumulate over time. The space station environment causes cognitive decline. Executive function deteriorates. Sustained attention weakens. Processing speed slows. These are the exact cognitive domains most critical for mission safety and interpersonal regulation. As your ability to think clearly diminishes, your ability to handle emergencies and get along with crewmates also declines. This creates a vicious cycle. Stress impairs cognition. Impaired cognition causes mistakes. Mistakes create more stress. In a 6-month mission, this cycle has time to stabilize or be managed. In a 40-year mission, it compounds until crew members are operating at significantly reduced mental capacity compared to when they launched. The interpersonal dynamics alone could doom a mission. Choose your crewmates carefully because you're stuck with them for life. Personality conflicts that would be annoying on Earth become catastrophic in space. There's no walking away, no changing jobs, no moving to a different city. You're in a confined space with the same people day after day, year after year, decade after decade. Antarctic research stations report that the isolation doesn't cause problems immediately. The first months are often fine. It's the long middle stretch where psychological issues emerge. People stop communicating effectively. Small irritations become major grievances. The environment stops being novel and becomes oppressive. Now extend that timeline by a factor of 30 or 40. What happens in year 12 when you still have 28 years to go? How do you maintain psychological health when you're not even halfway through a journey that's already lasted longer than some people's entire careers? The sensory monotony is another factor nobody talks about enough. Same walls, same sounds, same smells, same people, same tasks. Day after day. The human brain craves novelty. We're wired to seek new experiences, new information, new stimulation. Deprive someone of that long enough, and their mental health deteriorates regardless of other factors. You might think virtual reality could help. Create simulated environments, give crew members the illusion of variety. Maybe. But VR requires computing power, which requires energy, which brings us back to power generation limitations. And there's a limit to how much simulated experience can replace actual experience. Eventually, your brain knows it's not real. The illusion stops working. Sleep becomes another casualty. Circadian rhythm disturbance is already a problem on the ISS, where astronauts see 16 sunrises per day. On a Kuiper Belt mission, there's no sun to regulate your internal clock. You're in perpetual darkness or perpetual artificial light. Your body loses its natural rhythm. Sleep quality degrades. Fatigue accumulates. Cognitive function deteriorates further. The psychological research suggests that what we're dealing with isn't just isolation or confinement or stress. It's the convergence of all these factors simultaneously in an environment fundamentally incompatible with how human neurobiology evolved. We developed in environments with day-night cycles, seasonal changes, social groups larger than 6 people, the ability to leave stressful situations, connection to nature, fresh air, natural light. Remove all of that for 40 years, and you're conducting an experiment never attempted in human history. No amount of training prepares someone for that. You can't train yourself to need less social contact. You can't train your brain to stop requiring novel stimuli. You can't train your circadian rhythm to function without external time cues. Some propose rotating crew members in shifts, part of the crew in stasis, while others remain awake. This solves nothing. You still need the same number of total crew years of consciousness. You're just distributing them differently. And you're adding the psychological burden of watching some crew members age while others don't, of missing years of mission time while in stasis, of the anxiety about whether you'll wake up properly. The comparison to long sea voyages falls apart under examination. Sailors on multi-year voyages could see the ocean, feel the wind, catch fresh fish, stop at ports. They had variety even in confinement. They had natural light and weather. They had the knowledge that land existed somewhere beyond the horizon. A spacecraft offers none of this. It's more like being sealed in a submarine that never surfaces, except submarines return to port regularly. What makes this particularly tragic is that we can't even properly study the problem. You can't ethically confine people in a spacecraft simulator for 40 years to see what happens. You can't replicate the psychological reality of knowing there's no escape, no rescue, no going home early. Every simulation is fundamentally different from the real experience. The data we do have suggests the problem is unsolvable with current understanding. Anxiety and depression rates among astronauts increase with mission duration. Cognitive decline increases with time in space. Interpersonal conflicts escalate the longer people are confined together. Every trend points in the wrong direction for a multi-decade mission. You might find individuals psychologically robust enough to handle a year in deep space, maybe even 2, but 40. The psychological durability required doesn't exist in the human population because it was never selected for evolutionarily. Our ancestors never needed to survive that kind of isolation. Natural selection didn't prepare us for it. This is where the conversation usually shifts to genetic engineering or pharmaceutical interventions. Maybe we could modify humans to need less social contact, to handle isolation better, to maintain cognitive function in adverse conditions. Sure, maybe. But now you're not sending humans to the Kuiper Belt. You're sending genetically modified post-humans. That's a different ethical and practical discussion entirely. Even if such modifications were possible and ethical, the timeline doesn't work. Developing, testing, and implementing genetic modifications for deep space psychology would take generations of research. You can't test whether a modification works for 40-year missions without running 40-year missions. The feedback loop is impossibly long. The pharmaceutical approach fails for similar reasons. You can't keep people on psychiatric medications for 40 years without serious side effects. Tolerance develops, effectiveness decreases, withdrawal becomes dangerous. You'd need to bring enough medication for 4 decades, accounting for degradation, and hope nothing goes wrong with storage or dosing. What you're left with is an unbridgeable gap between human psychological capabilities and mission requirements. We evolved for life on Earth in social groups with natural environments and sensory variety. A Kuiper Belt mission offers none of these things and can't be engineered to provide them within the constraints of spacecraft design, power budgets, and mission parameters. The mind breaks before the body in these scenarios. You could theoretically solve radiation shielding, bone loss, life support, but you can't solve human psychology because you can't redesign the human brain with current technology. The psychological barrier isn't an engineering problem. It's a fundamental mismatch between what humans are and what the mission requires them to be. Which brings us to life support, the invisible umbilical cord connecting astronauts to survival. Every breath you take right now is free. The oxygen just exists around you, constantly replenished by billions of trees and trillions of phytoplankton. Water falls from the sky. Food grows from dirt. These aren't luxuries. They're background processes Earth handles automatically without you thinking about them. A spacecraft to the Kuiper Belt offers none of this. Each crew member needs roughly 5 kilograms of consumables daily. That's 0.84 kilograms of oxygen, 0.62 kilograms of food, and 3.54 kilograms of water. Doesn't sound like much until you multiply by crew size and mission duration. For 6 people on a 30-year mission, you're looking at over 200,000 kilograms of supplies. That's 200 metric tons, more than the entire mass of most spacecraft ever launched. You can't bring it all. The rocket equation makes that impossible. Every kilogram of payload requires exponentially more fuel to launch. There's no configuration where you pack 40 years of food, water, and oxygen for a crew and still have room for engines, fuel, shielding, or the crew themselves. So you recycle. The International Space Station's Environmental Control and Life Support System can recover about 98% of water. Sounds impressive until you examine what that means over decades. The water processor assembly actually has a 15.3% loss rate before accounting for other system inefficiencies. Even achieving 98% efficiency requires constant filter replacements, maintenance, and monitoring. On the ISS, when filters fail, new ones arrive on the next cargo ship. When systems break, replacement parts come up on the next Dragon capsule. When something goes catastrophically wrong, the crew can evacuate to Earth within hours. None of that works for the Kuiper Belt. A 2% loss rate sounds trivial, barely noticeable, but compound it over 40 years with no resupply, and you're watching your crew slowly dehydrate to death. You can't carry enough spare filters for 4 decades. You can't stockpile enough backup components for every possible failure mode. You can't maintain 98% efficiency when systems degrade, seals fail, and equipment ages in ways we can't fully predict. The math becomes horrifying quickly. Current closed-loop systems cannot achieve 100% recycling efficiency. Thermodynamics won't allow it. Every process loses something. Water vapor escaping during maintenance. Trace elements binding to filters. Organic compounds breaking down into unrecoverable forms. The cost of recycling increases dramatically as you approach 100% closure. Any system less than perfectly efficient depletes over time. Your water reserves shrink. Oxygen levels drop. The buffer that keeps you alive gets thinner year after year until one minor malfunction becomes a death sentence. Then there's food. The ISS doesn't grow its own food. Astronauts eat packaged meals shipped from Earth. That's sustainable for 6-month rotations. For 40 years, you'd need to grow food aboard the spacecraft, which means bringing an entire agricultural system into deep space. Plants need light, lots of it, water, nutrients, atmospheric control, temperature regulation. The energy requirements alone would overwhelm power generation capabilities. You're running grow lights 24/7 for crops, while simultaneously powering life support, propulsion, communications, heating, and everything else. CELSS, Controlled Ecological Life Support Systems, require energy input comparable to physicochemical systems just to produce biomass. Plus, they generate low-grade heat that must be removed from the spacecraft. In the vacuum of space, heat removal is brutally difficult. You can't open a window. You can't install an air conditioner. Heat rejection requires radiators, and radiators add mass, and mass makes the mission harder. Bioregenerative systems sound elegant in theory. Grow plants that produce oxygen and food while consuming carbon dioxide and waste. Close the loop. Create a tiny ecosystem. But ecosystems are fragile. They crash. Crops fail. Diseases spread. Contamination events wipe out entire harvests. On Earth, one bad season means you import food from elsewhere. In deep space, one crop failure means starvation. There's no backup farm, no emergency food delivery, no margin for error. You might maintain hydroponics successfully for a year, maybe 2, but 40? With no replacement seeds, no new soil nutrients, no way to compensate when something in the biological cycle breaks. Current systems can't achieve that reliability. The waste problem compounds everything. A Mars mission with 6 crew for 180 days generates 1,825 kilograms of solid waste, occupying 28.5 cubic meters. That's for half a year. Scale it to 40 years, and you're generating over 100,000 kilograms of waste. Inedible plant biomass, food residue, paper, plastic, cardboard, wastewater concentrates, urine concentrates, feces. Where does it go? You can't jettison it. That's wasting mass that took enormous energy to accelerate. You can't store it indefinitely. The spacecraft isn't a warehouse. You need to recycle it, but current systems don't recover organic waste effectively. The ISS simply discards fecal and food wastes instead of recycling them. That's not acceptable for deep space. Those wastes contain critical elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, needed for ongoing food production. Losing them means watching your closed-loop system slowly open as essential elements leak away into waste you can't process. The engineering challenge isn't just difficult, it's layered impossibilities stacked on top of each other. You need near-perfect recycling that current technology can't achieve. You need reliable food production that has never been demonstrated long-term. You need waste processing that doesn't exist. You need all of it to function flawlessly for decades, without maintenance, without replacement parts, without any of the support infrastructure that makes these systems marginally functional on the ISS. One component failing cascades through the entire system. Water recycling breaks down, so you use stored reserves, so you have less buffer, so the next failure hits harder, so you ration water, so hygiene suffers, so disease spreads, so immune systems already compromised by radiation and microgravity fail faster, so crew health deteriorates, so their ability to maintain systems decreases, so more failures occur. It's a death spiral with no exit. You can't design around it because you can't predict every failure mode across 4 decades. Equipment fails in unexpected ways. Seals degrade. Electronics degrade. Mechanical components wear out. Filters clog. Pumps seize. Valves stick. Every system has a mean time between failures, and over 40 years, you'll exceed it multiple times for every component aboard. The Space Shuttle's life support system was designed for 2-week missions. The ISS gets constant resupply and maintenance. No life support system has ever operated in space for even a single year without external support. We're talking about 40 years minimum. Compare that to submarines, which seem like a reasonable analog. Nuclear submarines stay submerged for months at a time with crews of over 100. They recycle air and water. They operate in isolation. But submarines surface regularly. They return to port for maintenance. They operate in an environment where rescue is possible. Crew rotations happen. Fresh supplies come aboard. A Kuiper Belt spacecraft has none of these options. You can't surface. You can't dock at a port. Rescue is impossible. The crew that launches is the crew that's stuck there for 40 years. No rotation, no resupply, no maintenance beyond what the crew can perform with whatever spare parts they brought. Submarines also benefit from the ocean's thermal mass for cooling. They have access to seawater for ballast and thermal regulation. They operate in Earth's magnetic field with some radiation protection. They're minutes or hours from help if something goes catastrophically wrong. The spacecraft analogy people love, comparing this to the Apollo missions, falls apart under any scrutiny. Apollo missions lasted days. The longest was 12 days for Apollo 17. You can survive almost anything for 12 days. You can tolerate bad food, cramped quarters, minimal hygiene, sleep deprivation, stress. It's temporary. 40 years isn't temporary. It's your entire adult life. You can't maintain Apollo-level deprivation for 40 years. The human body breaks. The mind breaks. Systems that worked for days fail over decades. There's also the power problem. Life support requires constant energy, water recycling, air circulation, temperature control, food production, waste processing. Every system draws power continuously. The spacecraft needs to generate this power reliably for 40 years. Solar panels don't work in the outer solar system. At the Kuiper Belt, sunlight is 900 to 2,500 times weaker than at Earth. You'd need solar arrays the size of football fields to generate meaningful power, and the mass makes that impossible. Radioisotope thermoelectric generators degrade over time. The Voyager spacecraft lose about 4 watts of power annually as their plutonium decays. After 46 years, they've lost substantial generating capacity. They're still functioning, barely, running only essential instruments. A human mission needs orders of magnitude more power, not for instruments, but for keeping people alive. Nuclear reactors sound promising until you examine the requirements. You need a reactor that operates autonomously for decades in the vacuum of space, while providing consistent power for life support. No such reactor exists. No reactor has been designed for this mission profile. Testing would take decades. Development would take decades. You'd need to solve heat rejection in vacuum, shielding for both crew and electronics, fuel that lasts 40 years, and fail-safe mechanisms that work without ground support. Even assuming you could build such a reactor, you're adding mass, complexity, and new failure modes. Reactors require cooling. Cooling requires radiators. Radiators add more mass. The spacecraft keeps getting heavier, requiring more fuel, requiring a bigger rocket, requiring more development time and cost. None of the numbers work. Every solution creates new problems. Every system depends on other systems that can't be made reliable enough. The dependencies form an impossible web, where failure anywhere threatens failure everywhere. Life support isn't a solved problem we're scaling up. It's an unsolved problem that gets exponentially harder with mission duration. The difference between 6 months on the ISS and 40 years to the Kuiper Belt isn't incremental. It's categorical. You're not doing the same thing for longer. You're attempting something fundamentally different that requires technology we don't have and might not be able to develop within physical and economic constraints. This is where optimists point to future technology. Better recycling systems, more efficient power generation, advanced food production. And sure, maybe those technologies get developed eventually, but eventually doesn't help. The physics of the Kuiper Belt doesn't change while we wait for better technology. You still need near-perfect efficiency for 40 years. You still need systems that never fail. You still need to solve problems that compound over time instead of remaining static. Better technology might push the boundaries, but it doesn't eliminate fundamental constraints. The real killer is that you can't test these systems properly. You can't run a 40-year life support test on Earth because Earth provides too many escape hatches. If something fails in a ground test, you open the door and bring in replacement parts. The psychological pressure isn't the same. The inability to resupply isn't the same. The radiation environment isn't the same. The microgravity effects aren't the same. You can simulate components, but you can't simulate the system operating under actual mission conditions for actual mission duration. Which means you're launching humans on a 40-year journey with life support systems that have never been proven to work for 40 years under those specific conditions. That's not engineering. That's gambling with human lives, using untested systems on a scale where failure means death, and there's no rescue coming. The psychological dimension deserves its own examination because it represents a category of failure that technology can't solve. You can engineer better shielding. You can design more efficient recyclers. You can't engineer away the human mind's response to isolation that stretches across decades. Start with something simple. Communication delay. On the ISS, astronauts talk to their families in real time. There's psychological support available immediately when needed. Mission control responds to questions within seconds. That connection to Earth, that lifeline to home, matters more than most people realize. Mars changes that equation. Communication delays reach up to 44 minutes round trip. You ask a question, wait 22 minutes for it to reach Earth. Wait another 22 for the response. Conversations become exchanges of recorded messages. Psychological crises can't be addressed in real time, but you're still talking to Earth within the same day. The Kuiper Belt multiplies that delay by factors of 10 or more. At 30 astronomical units, you're looking at 4 hours one-way minimum, 8 hours for a response. At 50 astronomical units, it's nearly 7 hours each way, 14 hours for any interaction with Earth. You send a message in the morning, maybe get a response the next day. Maybe. That delay does something to the human psyche. Earth becomes an insignificant bluish-green dot in the heavens, the Earth out of view phenomenon. You're watching your home planet shrink until it's indistinguishable from the stars. Everything you've ever known, everyone you've ever loved, reduced to a point of light that eventually disappears entirely. Now imagine living with that for 40 years. The isolation statistics from current missions provide a baseline, but they're misleading because they come from 6 to 12-month missions where astronauts can see Earth from their windows. NASA found that 85% of female astronauts showed anxiety symptoms. 43% showed depression symptoms. Those numbers come from relatively short stays on the ISS with Earth always visible. One cosmonaut, Lebedev, struggled with depression after only 7 months aboard a space station. 7 months. A Kuiper Belt mission isn't measured in months, it's measured in decades. The psychological stressors compound in ways that don't happen on shorter missions. You've got microgravity affecting your body, constant noise from life support systems, circadian rhythm disturbances because there's no natural day-night cycle, complete isolation from everyone except your crewmates, confinement in a space smaller than most apartments, no privacy, no escape, no variation in environment. And here's what makes it truly devastating. It's relentless. There's no weekend off, no vacation, no walking outside, no new faces, no change in scenery. The same walls, the same people, the same sounds, the same routine, for 40 years. Research shows this convergence of isolation, confinement, sensory monotony, interpersonal friction, and mission-critical cognitive demand creates an environment fundamentally incompatible with human neurobiology as it evolved. From a cognitive standpoint, you see declines in executive function, sustained attention, and processing speed, exactly the domains most critical for mission safety and interpersonal regulation. The environment doesn't have to be catastrophic to be psychologically erosive. It simply has to be relentless. Think about interpersonal dynamics. You're locked in a small spacecraft with 3 to 5 other people. These are the only humans you'll interact with for decades. Every annoying habit gets magnified. Every personality quirk becomes unbearable. There's no walking away, no cooling off period, no distance. Studies of Antarctic research stations show that even in relatively comfortable conditions with regular resupply and eventual extraction, people crack. Fights break out. Depression sets in. Cognitive function deteriorates. And those missions have endpoints measured in months, not decades. A Kuiper Belt crew would experience something unprecedented in human history. Longer isolation than any polar expedition, more confinement than any submarine voyage, greater distance from help than any previous human endeavor, with stakes that don't allow for psychological breakdown. Consider what happens when someone develops severe depression or anxiety 10 years into the mission. You can't evacuate them. You can't send a replacement. You can't provide in-person therapy. The medication you brought is degrading. The psychological support from Earth is delayed by hours. The person still has to function because the mission depends on everyone performing their duties. What happens when interpersonal conflicts escalate to the point where crew members refuse to work together? You can't separate them. You can't transfer anyone to a different assignment. You can't bring in a mediator. The conflict just festers for years while the mission continues. What about cognitive decline from radiation exposure? The brain takes damage from cosmic rays. Executive function deteriorates. Memory becomes unreliable. Decision-making abilities decline. But the mission requires constant vigilance and complex problem-solving. There's no backup crew, no relief operators, just people with increasingly compromised cognitive abilities trying to keep themselves alive. The psychological research makes this clear. The mission duration we're discussing exceeds any established psychological endurance limits. We don't have data on how humans respond to 40 years of isolation because no one has ever experienced it. We're extrapolating from missions lasting months and assuming the trend continues linearly. But psychological deterioration isn't linear. It accelerates. You might think careful crew selection solves this. Choose psychologically resilient individuals. Screen for mental health issues. Pick people who work well together. And yes, that helps initially, but 40 years breaks anyone. Resilience isn't infinite. Even the most mentally strong individuals have limits. The selection process itself creates problems. You need people young enough to survive the journey, but experienced enough to handle the technical demands. You need specialists in multiple fields, but a crew small enough to minimize resource consumption. You need people who can work together for decades, but diverse enough perspectives to solve unexpected problems. The requirements contradict each other. Then there's the question of informed consent. How do you ethically recruit people for a mission they might not survive? A mission that will definitely damage their health. A mission that will consume their entire adult life. You're asking people in their 20s to commit to something that won't end until they're in their 60s, assuming they survive. What about families? Do crew members leave spouses and children behind, knowing they'll miss decades of their lives? Do they launch with families aboard, subjecting children to an environment that will stunt their physical and psychological development? Neither option is ethical. Neither option works. The volunteer pool for such a mission would be tiny. You'd be selecting from people willing to sacrifice their entire lives for a journey that offers no personal benefit beyond the abstract satisfaction of exploration. Most qualified individuals wouldn't accept those terms. You'd end up with either true believers willing to die for the cause or people with nothing to lose. Neither category ideal for a mission requiring decades of stable, rational decision-making. And here's something people don't consider. The mission itself becomes meaningless over time. The initial excitement fades. The scientific objectives that seemed so important at launch become abstract concepts disconnected from daily survival. You're not exploring anymore. You're just enduring. Just trying to stay alive long enough to reach an arbitrary destination that has no significance beyond the fact that someone decided you should go there. The human mind needs meaning to function. It needs purpose beyond mere survival. On Earth, even in difficult circumstances, people find meaning through relationships, through work, through contributing to something larger than themselves. On a Kuiper Belt mission, those sources of meaning evaporate. Your relationships are limited to a handful of people you're tired of. Your work is maintaining systems that keep you alive. Your contribution is suffering for decades, so that maybe, possibly, humanity learns something interesting about distant rocks. That's not enough to sustain the human psyche for 40 years. The psychological challenges alone make a Kuiper Belt mission impossible with current understanding of human psychology. And unlike technical problems, you can't engineer around psychological limitations. You can't build a better brain. You can't upgrade someone's resilience. You can't patch mental health issues with software updates. This brings us to the final, most fundamental barrier, one that doesn't get discussed enough because it's so obvious it seems redundant to mention. But it's worth stating explicitly because it underlies everything else. Human lifespan. A realistic Kuiper Belt mission using any technology we can envision within the next century requires 40 to 80 years for a round trip. Let that number sink in. 40 to 80 years. That's not a career. That's an entire lifetime. Astronauts would need to launch in their 20s or early 30s to have any hope of surviving the journey. They'd return, if they returned at all, as elderly individuals. Their entire adult life spent in a metal tube hurtling through space. Everything they knew before launch would be gone. Everyone they left behind would be dead or unrecognizably aged. They'd return to a world that had moved on without them. The longest anyone has spent continuously in space is 438 days, 14.5 months, less than half the desired time frame for a Mars mission. We're talking about extending that by a factor of 20 or 30. We have no data on what happens to humans after 5 years in space, let alone 40. You might think generational ships solve this problem. Launch a crew knowing they won't survive to arrival. Their children continue the mission. Their grandchildren reach the destination. But that introduces new nightmares. You're condemning people born in space to a life they never chose. Children who will never see Earth, never experience gravity, never have options beyond continuing a mission they didn't sign up for. The ethical problems are staggering. The practical problems are worse. How do you maintain genetic diversity with a small founding population? How do you prevent inbreeding over multiple generations? How do you ensure children receive adequate education and socialization? How do you handle medical emergencies involving pregnant women and infants in microgravity? How do you manage population growth in a fixed-size habitat? None of these questions have good answers. Some don't have any answers. We're speculating about social engineering on a scale never attempted, in an environment never tested, with consequences that are irreversible. And that's before considering the technology barriers that make the entire concept scientifically questionable at best. You'd need rotating habitats to simulate gravity, structures never built, never tested with humans for more than a few months. The engineering challenges are absurd. A rotating cylinder large enough to house 4 to 6 people comfortably, spinning fast enough to generate Earth-like gravity without inducing nausea, while maintaining structural integrity for 40 years. The bearings alone would be a nightmare. Any imbalance causes wobble. Wobble causes stress. Stress causes failure. And you can't exactly call a repair technician when you're 3 billion miles from Earth. Then there's the question of who maintains genetic records, medical histories, educational curricula. Who decides which culture gets preserved, which language gets taught, which values get transmitted? You're not just sending astronauts. You're creating a new society from scratch with zero margin for error and no external input for decades. But let's say you solve all that. Somehow, through engineering breakthroughs we can't currently imagine, and social engineering we've never successfully attempted. You still face one insurmountable problem that no amount of technology can fix. Physics. The universe has speed limits. and they're not suggestions. New Horizons, the fastest spacecraft ever launched toward the outer solar system, took 9.5 years just to reach Pluto. That's with no crew, no life support, no return capability, using gravity assists from Jupiter that shaved years off the journey. A crewed mission can't use those same aggressive trajectories. You need gentler accelerations, more conservative flight paths, redundant systems that add mass, which requires more fuel, which adds more mass, which requires even more fuel. It's the tyranny of the rocket equation. Every kilogram of payload requires exponentially more fuel. Life support systems are heavy. Radiation shielding is heavy. Food for 40 years is heavy. Water recycling equipment is heavy. The habitat itself is heavy. Power generation systems are heavy. By the time you've added everything humans need to survive, your spacecraft masses thousands of tons. Chemical rockets can't move that much mass fast enough. The fuel requirements become absurd. You'd need a spacecraft the size of a skyscraper just to carry enough propellant, which itself requires more propellant to accelerate, which requires more propellant to accelerate that propellant. The math spirals into impossibility. Electric propulsion offers better efficiency but pathetic thrust. Ion drives produce less force than the weight of a single sheet of paper. They can run for years, gradually building speed, but they require enormous amounts of electrical power. Where does that power come from? Solar panels are useless beyond Mars. The sun is too dim. You'd need panels the size of football fields to generate meaningful power, which adds mass, which requires more propellant, and we're back to the same spiral. Nuclear propulsion sounds promising until you examine the details. Nuclear thermal propulsion uses a reactor to superheat hydrogen and expel it for thrust. Better than chemical rockets, more powerful than ion drives, but still not fast enough. You'd still be looking at decades of travel time. And that's assuming you solve the political nightmare of launching a nuclear reactor, the engineering nightmare of cooling it in space, the safety nightmare of operating it near humans, and the fuel nightmare of keeping it running for 40 years. Nuclear pulse propulsion, detonating nuclear bombs behind your spacecraft for thrust, offers genuinely fast travel times. Project Orion calculations suggested you could reach significant fractions of light speed, but the engineering is insane. You're setting off thermonuclear explosions meters from your crew. The acceleration forces would be brutal. The radiation exposure would be fatal. The political obstacles would be insurmountable. And we've never built anything remotely like it. Fusion propulsion remains theoretical. We haven't achieved sustained fusion reactions on Earth yet, let alone in a compact spacecraft reactor. Even if we solve fusion tomorrow, miniaturizing it for space travel and making it reliable enough for a 40-year mission is a separate challenge that could take centuries. Antimatter propulsion offers the highest theoretical efficiency, but we produce antimatter in quantities measured in atoms. Creating enough antimatter to fuel a spacecraft would require more energy than humanity currently generates annually, and storing it without letting it touch normal matter and annihilate is a problem we haven't remotely solved. Which brings us to the reality nobody wants to acknowledge. Every propulsion technology advanced enough to make a Kuiper Belt mission feasible doesn't exist. Not in prototype form, not in testing, not even in detailed design. We have equations on paper and optimistic assumptions. That's it. The fastest we've ever moved a human-made object away from the Sun is Voyager 1, traveling at 38,000 miles per hour. Sounds fast. It's not. At that speed, reaching the Kuiper Belt takes decades. Returning takes decades more. You need to go faster, much faster. But increasing speed requires exponentially more energy, and we've already established that energy is the limiting factor. Even if fusion propulsion worked perfectly tomorrow, you're still looking at 20 to 30 years minimum for a one-way trip. Add the return journey, and you're back to lifespans exceeding human working careers. Some suggest suspended animation solves the time problem. Put the crew to sleep, wake them up at the destination. Sounds great, completely unsolved medically. We can't keep humans in suspended animation for days, let alone years. Every attempt at inducing hypothermia for medical procedures works for hours, not decades. The cellular damage from extended stasis would be catastrophic. Ice crystals form in cells, shredding them from the inside. Metabolic processes don't just slow, they fail. Organ systems shut down. And even if you somehow preserved the body perfectly, you'd still need to maintain it, monitor it, protect it from radiation, keep the suspension equipment functioning for 40 years without maintenance. The technology doesn't exist. It's not close to existing. It's speculative science that might violate fundamental biology. But let's ignore physics, biology, engineering, and psychology for a moment. Let's pretend we solve every technical challenge through some miraculous breakthrough. You still face the economic reality that makes a Kuiper Belt mission politically impossible. A Mars mission is estimated to cost somewhere between $500 billion and $1 trillion. That's for a destination 40 million miles away at closest approach. The Kuiper Belt is 100 times farther. The costs don't scale linearly, they scale exponentially. More distance requires more fuel, more shielding, more redundancy, more everything. A realistic cost estimate for a Kuiper Belt mission would be measured in trillions, multiple trillions. Money that could instead fund thousands of robotic missions, cure diseases, address climate change, educate billions of people. No government will fund it. No combination of governments will fund it. The return on investment is zero. You spend decades and trillions of dollars to send people to empty space to look at rocks we can study with robots for a fraction of the cost. There's no economic incentive, no strategic value, no resource to extract that justifies the expense. Private funding won't materialize either. Billionaires fund Mars missions because Mars has cultural cachet. It's the next frontier, potential colony, backup planet. The Kuiper Belt has none of that. It's cold, dark, empty space, 4 billion miles away. There's no brand value, no publicity, no return on investment beyond abstract scientific knowledge that robots can acquire cheaper. Which leads to the final, most damning reality. We don't need to send humans to the Kuiper Belt. Everything we want to learn can be learned with robotic probes. New Horizons taught us more about Pluto in one flyby than humans could learn in a decade of orbital study. Future probes will map the Kuiper Belt comprehensively. They'll sample objects, analyze compositions, measure magnetic fields, return data that answers every scientific question we have. Robots don't need life support, don't need food, don't need psychological counseling, don't complain about confinement, don't develop cancer from radiation, don't lose bone density, don't require return trips. You send them on one-way missions that cost millions instead of trillions and return better science because they can take risks humans can't. The romantic notion of human exploration sounds inspiring until you examine what humans actually contribute beyond their presence. Scientific instruments don't care who operates them. Data collection doesn't require biological intelligence. Sample analysis can be automated. The only thing humans add is vulnerability. Thousands of ways the mission can fail because biology is fragile and space is hostile. Every argument for human presence in the Kuiper Belt collapses under scrutiny. Scientific value? Robots are better. Inspiration? Watching people suffer for 40 years isn't inspiring. Survival of the species? The Kuiper Belt isn't habitable. Technological advancement? We'd advance faster spending those trillions on Earth-based research. The Kuiper Belt mission isn't just difficult. It's not just expensive. It's not just dangerous. It's pointless. A solution in search of a problem. An answer to a question nobody's asking. We're not refraining from sending humans because we lack courage or vision. We're refraining because it would be an act of profound stupidity to sacrifice human lives and vast resources for zero meaningful return. So we're left with the inescapable conclusion that this mission serves no purpose. But maybe you're thinking there's one final card to play. One last technological breakthrough that could change everything. Artificial intelligence, automation, self-repairing systems. Except those don't solve the fundamental problems. They create new ones. Let's say we develop AI sophisticated enough to manage life support autonomously, diagnose problems, execute repairs, make decisions without human intervention. Sounds promising until you realize what that actually means for a Kuiper Belt mission. First issue, control. You're 4 billion miles from Earth with communication delays of 4 to 7 hours each way. The AI encounters a situation requiring human judgment. It sends a query. 7 hours later, Earth receives it. Mission Control deliberates. 7 hours after that, their response arrives. 14 hours for a single exchange. By then, the crisis has either resolved itself or killed everyone aboard. So the AI needs full autonomy, complete authority over life or death decisions. You're entrusting your survival to software for 40 years with no possibility of override or intervention. Every edge case, every unexpected failure mode, every scenario the programmers didn't anticipate must be handled by algorithms that can't be updated once you're beyond radio range. Now consider what happens when the AI makes a mistake. Because it will. All software has bugs. All systems have failure modes. On Earth, we patch them, update code, learn from errors. 4 billion miles from Earth, there's no patch, no update, no second chance. The Mars rover Curiosity has been on Mars since 2012. NASA has sent numerous software updates to fix bugs and add functionality. That's possible because Mars is close enough for regular communication and the rover doesn't have humans depending on it for survival. A Kuiper Belt spacecraft can't receive updates once communication lag exceeds practical limits. Whatever software launches with the mission is what the crew lives with for decades. Then there's the hardware problem. Self-repairing systems sound revolutionary until you ask what they actually repair with. Every spare part must be carried from Earth. Every component that might fail needs a backup. Then a backup for the backup. The mass compounds exponentially. A 3D printer could manufacture replacement parts from raw materials. Except the printer itself needs maintenance. The raw materials have mass. The designs must account for every possible failure. And some components can't be printed. Computer chips, sensors, high-precision instruments. Those must be carried as spares, each adding mass the mission can't afford. Some futurists propose nanotech repair systems, molecular assemblers that could rebuild anything from base elements. That technology doesn't exist, won't exist for decades, might never exist in the form required. Banking a mission on science fiction isn't planning, it's wishful thinking. Here's what self-repair actually looks like in practice. The International Space Station, humanity's most advanced orbital facility, regularly serviced by supply missions, staffed by trained engineers, supported by thousands of ground personnel, still experiences constant failures requiring human intervention and shipped parts. Multiply the ISS failure rate by 40 years with no resupply, and you're not maintaining systems. You're watching them gradually fail while hoping the critical ones last longest. That's not a mission. That's a countdown to catastrophe. But let's assume, generously, that we solve all the AI problems. Perfect software, unlimited spare parts, flawless automation. We still haven't addressed the human element, because humans break in ways machines can't fix. Psychological deterioration doesn't respond to algorithms. When an astronaut develops clinical depression 20 years into the mission, no amount of automation helps. When interpersonal conflicts escalate to violence in an inescapable confined space, AI can't mediate effectively. When someone decides they can't endure another 20 years and wants to end their life, software doesn't provide meaningful intervention. Earth out of view phenomenon becomes catastrophic on a Kuiper Belt mission. Mars astronauts will watch Earth shrink to a star-like point. Kuiper Belt astronauts will watch it disappear entirely. The psychological impact of being the most isolated humans in history, while trapped in a metal tube for 40 years, exceeds anything our species has experienced. Antarctic research stations provide the closest analog we have. Isolated crews in hostile environments for extended periods. Even with the knowledge that rescue is theoretically possible and the mission has a definite end date, people break. Depression, substance abuse, interpersonal violence, all documented repeatedly in Antarctic research. Now remove the possibility of rescue. Extend the timeline to decades. Eliminate any visual connection to Earth. Add the constant knowledge that the slightest system failure means death. The psychological pressure becomes unbearable. Some propose psychological screening to select resilient individuals. NASA already does this. They select the most psychologically stable candidates available. Those candidates still experience anxiety and depression on 6-month ISS missions where they can see Earth and video call family. No amount of screening identifies who will maintain psychological stability for 40 years in isolation. Human psychology doesn't work that way. We're social animals evolved for Earth environments. Extended isolation in artificial environments breaks us regardless of initial stability. Training helps. For short missions. For 6 months, astronauts can rely on training and discipline. For 40 years, training becomes irrelevant. You're not executing procedures anymore. You're living a life where every single day is identical to the last, where nothing changes except systems slowly failing and your body gradually breaking down. Medication could help manage psychological symptoms. Except medications have expiration dates, storage requirements, side effects that compound over years. You'd need enough psychiatric medication for multiple people for 40 years with no possibility of adjusting prescriptions based on response. That's not treatment. That's guessing and hoping. Entertainment might provide psychological relief. Books, movies, music, games, except you'd experience every piece of content dozens of times over 40 years. Novelty is essential for human psychological health. When everything is familiar, when nothing new ever happens, the mind deteriorates regardless of content quality. Virtual reality could theoretically provide novel experiences. Except VR hardware breaks, software has bugs, and fundamentally, you know it's not real. You're still in the same metal tube 4 billion miles from home. The illusion doesn't hold for decades. Some science fiction envisions suspended animation, sleep through the journey, wake up at arrival. Sounds elegant, except the technology doesn't exist. Induced hypothermia works for hours, not years. Actual suspended animation would require preventing cellular damage during freezing and thawing, a problem we haven't solved for single organs, let alone whole humans. Even if we could freeze people safely, someone needs to remain awake to maintain systems, which means shift rotations, which means some crew members experience the full psychological burden while others sleep. That's not distributing the hardship. That's concentrating it on whoever draws the short straw for watch duty. And suspended animation introduces new failure modes. What if the revival process fails? What if the systems maintaining suspension malfunction? You've just added complex technology with catastrophic failure consequences to a mission already drowning in complexity. Every proposed solution creates more problems than it solves. Every technological fix introduces new failure modes. Every system added increases mass and complexity. We keep trying to engineer our way around fundamental biological and physical limits that can't be engineered around. This is why serious mission planners don't propose human Kuiper Belt missions. Not because they lack imagination, because they understand constraints. The comparison to historical exploration is instructive. People often invoke Columbus or Magellan or polar explorers as examples of humans overcoming seemingly impossible challenges. Those comparisons are nonsense. Columbus sailed for weeks, not decades. His crew could breathe the air and drink rainwater. When ships leaked, carpenters repaired them with available materials. If someone got sick, they either recovered naturally or died. But the illness didn't threaten the entire crew's survival through cascading system failures. Magellan's voyage took 3 years. Terrible by sailing standards. Nothing compared to 40 years in a sealed environment where every breath depends on machines that can't be replaced. Antarctic explorers endured brutal conditions, but they were breathing Earth's atmosphere, protected by Earth's magnetic field, experiencing Earth's gravity. And they could see the horizon, feel wind, experience weather. They were isolated, not imprisoned in a metal tube watching themselves decay. The Kuiper Belt mission has no historical parallel because nothing in human experience approaches its challenges. We're not talking about pushing existing limits. We're talking about exceeding human biological capabilities by orders of magnitude. And here's the thing that makes all of this even more absurd. We don't need to do it. Every scientific question about the Kuiper Belt can be answered with robotic missions costing a fraction of human missions while returning superior data. New Horizons cost $700 million and transformed our understanding of Pluto. Future missions could comprehensively map the entire Kuiper Belt for tens of billions. Expensive by space mission standards, trivial compared to a human mission. Robots can sample surfaces, analyze compositions, measure magnetic fields, map gravitational anomalies. Return data that answers every question we have about Kuiper Belt formation, composition, and evolution. They do this better than humans because they don't need life support, don't complain about conditions, and can be designed for specific scientific tasks without compromise for human needs. The only thing humans add is vulnerability. Thousands of additional failure modes, massive cost increases, ethical complications when crew members die, all for no scientific benefit. So when people ask why we don't send humans to the Kuiper Belt, they're asking the wrong question. The right question is, why would we? What's the justification? What goal does human presence achieve that justifies the cost and risk? Science? Robots do it better. Inspiration? Watching people suffer isn't inspiring. Species survival? The Kuiper Belt isn't habitable. Resource extraction? Nothing there worth the cost. Technological development? We'd advance faster spending those resources on Earth. National prestige? Nobody cares about empty space 4 billion miles away. There is no justification. The mission serves no purpose except satisfying a romantic notion of human exploration that ignores practical reality. We're not avoiding the Kuiper Belt because we lack courage or vision or ambition. We're avoiding it because sending humans there would be an act of profound stupidity, sacrificing lives and resources for zero meaningful return. The honest answer to why no human will ever reach the Kuiper Belt alive is simple: because it would be pointless. And not just pointless, cruel. Because here's what nobody talks about when they romanticize deep space exploration: the ethical nightmare of actually doing it. You'd be asking people to volunteer for guaranteed suffering, decades of physical deterioration, cognitive decline, psychological torment, all while trapped in a metal cylinder they can never leave, surrounded by the same 5 people they'll grow to resent, watching their bodies betray them year after year. What kind of person volunteers for that? And more importantly, what kind of society asks them to? The volunteer pool would be self-selecting for either the profoundly mentally ill or the desperately suicidal. Psychologically healthy individuals don't choose guaranteed multi-decade suffering for no purpose. They don't abandon families, relationships, and any possibility of normal life to spend 40 years dying slowly in space. The mission would require screening out anyone rational enough to understand what they're signing up for. And that's assuming you could even find volunteers. You'd need backups, replacements for when crew members inevitably back out during training, which takes years. You'd need genetic diversity in case the mission becomes generational. You'd need specialists in multiple fields because you can't predict what will break. Medical doctors, engineers, biologists, psychologists, all willing to throw away their lives for nothing. Good luck with that recruitment drive. Then there's the funding problem. Conservative estimates for a Kuiper Belt mission start around $500 billion. Realistic estimates approach $1 trillion. For reference, the entire Apollo program cost about $280 billion in today's dollars, and that was just to the moon, 240,000 miles away. The Kuiper Belt is 4 billion miles away, 16 million times farther. NASA's annual budget is roughly $25 billion. The Kuiper Belt mission would consume 20 years of NASA's entire budget, every dollar, with nothing left for Earth observation, climate research, aeronautics, robotic missions, or anything else. And that's assuming zero-cost overruns, which never happens. The James Webb Space Telescope went 10 times over budget. The International Space Station cost 3 times initial estimates. Apply those multipliers to $1 trillion mission, and you're looking at spending that rivals entire national economies. For what? To say we did it? To plant a flag nobody will see? To satisfy some misguided notion that human exploration is inherently valuable, regardless of cost or outcome? The money alone kills the mission. But let's pretend it doesn't. Let's imagine some future civilization with unlimited resources and complete disregard for human welfare actually attempts this. They'd still fail because of something we haven't discussed yet: reliability engineering. Every system has a failure rate. Electronic components degrade. Mechanical parts wear out. Software develops bugs. On Earth, we fix things. In orbit around Earth, we send replacement parts. On the Moon, we might establish repair facilities. But 4 billion miles from Earth, you're on your own. The space shuttle had a catastrophic failure rate of about 1.5%, 2 losses in 135 missions. Those were missions lasting 2 weeks. A Kuiper Belt mission lasting 40 years is roughly 1,000 times longer. Even with vastly improved reliability, the probability of mission-ending failure approaches certainty. And it only takes one critical system failure. 1. The water recycler breaks and can't be repaired. Everyone dies of dehydration. The oxygen generator fails. They suffocate. Radiation shielding degrades. Cancer kills them slowly. The reactor malfunctions. They freeze. A micrometeorite punctures the hull in the wrong place. Explosive decompression. You can't carry enough spare parts for 40 years of operation. You can't predict every failure mode. You can't test systems for multi-decade reliability because you don't have decades to test them before launch. And you definitely can't troubleshoot complex failures remotely when communication delays stretch to 8 hours round trip. The crew would be alone, completely alone. And when something breaks, not if, when, they'd have to fix it themselves with whatever materials they have available, using skills they may not possess, under time pressure that could mean death in hours. This is what killed most historical expeditions. Not the journey itself, but equipment failure. Ships sank, supplies spoiled, navigation instruments broke. And those explorers had the advantage of being on Earth, where they could improvise using local materials, where rescue was at least theoretically possible, where they could breathe the air while making repairs. Space offers none of those advantages. The engineering challenge of 40-year reliability isn't just difficult. It's likely impossible with any physical technology. You'd need redundancy upon redundancy, backup systems for the backup systems, and those backup systems add mass, which requires more fuel, which requires bigger structures, which require more robust life support, which requires more power, which requires more shielding, which adds more mass. The spacecraft becomes impossibly large. Launch costs become impossibly high. And you still can't guarantee it won't fail. But let's keep pretending. Let's say some miraculous engineering breakthrough solves reliability. Let's say fusion power works. Let's say closed-loop life support achieves 99.9% efficiency. Let's say radiation shielding becomes lightweight. Let's say propulsion advances cut travel time to 20 years instead of 40. You still have the human problem. 20 years is still longer than any human has spent in space by a factor of 15. Longer than anyone has spent in any extreme environment. Longer than most marriages last. Longer than many careers. An astronaut launching at 30 would return at 50, if they returned at all. And during those 20 years, they age faster. Radiation accelerates cellular damage. Microgravity accelerates muscle and bone loss. Isolation accelerates cognitive decline. Stress accelerates cardiovascular disease. The 50-year-old who returns is biologically 60 or 70, assuming they survive the return to gravity, which their deteriorated body might not tolerate. You'd be sending healthy 30-year-olds and getting back broken 70-year-olds. If you're lucky. More likely, you're getting back corpses. Because the statistical probability of everyone surviving 20 years in deep space approaches 0. Someone develops cancer. Someone has a stroke. Someone's appendix ruptures. Someone develops a psychiatric break and becomes violent. Someone makes a critical mistake during a repair because their cognitive function has declined. And when people start dying, the mission dynamics change completely. Crew workload increases on survivors. Psychological stress intensifies. The sight of dead crewmates you can't bury, can't escape from, can't stop thinking about, that breaks people. Fast. Historical expeditions turn to cannibalism under less stressful conditions. So now we're not just sending people to suffer and die in space. We're sending them to watch each other suffer and die, to live with corpses, to face impossible decisions about resource allocation when supplies run low, to potentially fight each other when psychological breaking points are reached. This isn't exploration, it's torture. And for what? The Kuiper Belt contains ice and rock, things we have plenty of on Earth, things we can study remotely, things that don't justify human suffering. There's no valuable resources there, no rare elements worth the cost of retrieval, no strategic advantage to claiming territory, no scientific discoveries that require human presence, no benefit whatsoever that justifies the cost in money, resources, and human welfare. The Kuiper Belt mission fails every rational cost-benefit analysis. It fails ethically, it fails technically, it fails economically, it fails on every metric except, would it be cool? And cool isn't enough. This is why serious space agencies don't plan Kuiper Belt missions. Why no government allocates funding for them. Why engineers don't waste time designing them. Everyone who understands the actual requirements recognizes them as fantasy. The people advocating for this stuff are either ignorant of the challenges or deliberately ignoring them for rhetorical purposes. They're selling a vision that cannot be realized, promising a future that will not arrive, building expectations that will disappoint. Real space exploration focuses on achievable goals. The Moon is achievable. Mars is borderline achievable with significant advances. Asteroid mining might be achievable if economics work out. These missions have timelines measured in years, not decades. Distances measured in millions of miles, not billions. Risk profiles that are dangerous, but not suicidal. The Kuiper Belt has none of these characteristics. It's not the next step in human expansion. It's not a challenging but possible goal. It's a fundamental mismatch between human capabilities and mission requirements. And acknowledging that isn't pessimism. It's realism. It's recognizing that some things are genuinely impossible with human biology as it exists. That some destinations are genuinely unreachable with technology as it exists, or could plausibly exist. We can send robots to the Kuiper Belt. We have sent robots there. New Horizons is there right now, still functioning after nearly 20 years, still returning data, still expanding our knowledge. It didn't need life support, didn't need psychological counseling, didn't need exercise equipment or food or water or sleep. It just needed power and instruments and instructions. And it's doing better science than humans ever could, because it's optimized for science instead of survival. Future robotic missions will do even better. They'll carry more sophisticated instruments, sample collection systems, maybe even return capabilities. They'll map the entire Kuiper Belt, analyze dozens of objects, measure magnetic fields and compositions and orbital dynamics. They'll answer every question we have about that region of space, without killing anyone, without bankrupting anyone, without requiring technological miracles or ethical compromises. That's the real future of Kuiper Belt exploration. Robots doing what they do best while humans stay where they belong. On Earth, building the robots, analyzing the data, expanding knowledge without sacrificing lives. Some people find this disappointing. They want the romantic vision of human explorers pushing boundaries, planting flags, going where no one has gone before. They want Star Trek, not reality. But reality doesn't care about wants. Physics doesn't bend because we wish it would. Biology doesn't adapt because we need it to. Engineering doesn't magically solve problems that violate fundamental constraints. The Kuiper Belt is unreachable by living humans, not because we lack ambition or courage or vision. It's unreachable because the requirements exceed human capabilities by margins that no foreseeable technology can bridge. Because the mission profile guarantees suffering and likely death. Because the costs vastly exceed any possible benefits. This isn't a challenge to overcome, it's a limit to accept. And accepting limits isn't giving up. It's choosing wisdom over foolishness. It's directing resources toward achievable goals instead of impossible fantasies. It's respecting human life enough not to throw it away on pointless gestures. The honest answer remains: no human will ever reach the Kuiper Belt alive, because doing so would require becoming something other than human. Either cyborg entities that don't breathe or eat or age, or AI consciousnesses uploaded to machines, or perhaps distant descendants genetically engineered for space in ways we can barely imagine. But those wouldn't be humans anymore, not in any meaningful sense. They'd be our successors. And maybe that's fine. Maybe that's how intelligence spreads through the cosmos, not as biological organisms clinging to fragile bodies, but as something else entirely. But us, the humans reading this now, we're staying home. Our children are staying home. Their children are staying home. For generations to come, the Kuiper Belt remains what it's always been: a distant collection of icy rocks we study from afar, admire through telescopes, and leave to the robots purpose-built to explore it. That's not a failure of imagination. It's an acceptance of reality. And sometimes, reality simply says no. So that's the real answer. Not the one people want to hear, but the one that actually matters. No human will reach the Kuiper Belt alive, because the mission is fundamentally incompatible with human biology. The distance is too far, the timeline is too long, the environment is too hostile, the challenges compound too severely, and most critically, there's no reason to try. Every barrier we've examined isn't a temporary obstacle waiting for the right technology. These are hard limits written into the physics of space travel and the biology of human bodies. You can't engineer around the speed of light. You can't design away the need to breathe and eat and maintain bone density. You can't patch psychological deterioration with better software. The romantic vision of human explorers venturing to the edge of the solar system sounds inspiring until you actually calculate what it requires. Then it becomes clear we're not describing exploration. We're describing prolonged suicide. And for what? Ice and rock we can study remotely. Scientific questions robots answer better. A destination with no resources, no strategic value, no benefit that justifies the cost in human suffering and trillions of dollars. The people who understand orbital mechanics and radiation physics and life support engineering already know this. They've done the math, run the simulations, examined the requirements. That's why you don't see NASA planning crewed Kuiper Belt missions. Why no space agency anywhere has such missions in development. Why serious proposals focus on robotic exploration instead. Because robots are better at this. They don't need decades of supplies, don't deteriorate psychologically, don't require return trips, don't die when radiation exposure exceeds safe limits. They just go where we point them, collect data, and keep working until their power runs out. New Horizons proved this. Launched in 2006, arrived at Pluto in 2015, still functioning now as it explores deeper into the Kuiper Belt. Nearly 20 years of operation, no complaints, no psychological breakdowns, no life support failures, just consistent, reliable science from a probe that cost less than a single crewed mission to the Moon. That's the future of Kuiper Belt exploration. More sophisticated versions of New Horizons. Probes with better instruments, longer operational lives, maybe even sample return capabilities. Missions that cost millions or billions instead of trillions. Missions that return superior data without risking human lives. And that's okay. It has to be okay because it's reality. We don't get to choose which destinations are reachable by human crews. Physics makes that choice for us. Biology makes that choice for us. The math makes that choice for us. Accepting these limits isn't defeatism. It's rationality. It's recognizing that some challenges aren't meant to be overcome because overcoming them provides no value. It's understanding that human presence isn't inherently superior to robotic exploration when robots do the job better, cheaper, and safer. The Kuiper Belt will be explored thoroughly. We'll map it comprehensively, analyze its objects, understand its formation and evolution, answer every scientific question we have about that region of space. But we'll do it the smart way, with machines designed for the task instead of biological organisms struggling to survive in an environment that actively kills them. This doesn't diminish human achievement. It highlights human intelligence, the ability to recognize our limits and work within them, to build tools that extend our reach beyond where our bodies can go, to explore vicariously through technology rather than sacrificing lives on impossible journeys. Some people will always be disappointed by this answer. They want the Star Trek future, where humans boldly go everywhere, where distance and danger are just obstacles to overcome with enough determination, where every destination is eventually reachable if we just try hard enough. But that's fiction. Useful fiction that inspires us to attempt difficult things, but still fiction. Reality has constraints that don't disappear because we wish they would. The constraints on Kuiper Belt missions aren't temporary. They're not waiting for the next breakthrough. They're written into the fundamental structure of how space, time, and biology operate. And they're telling us clearly, This destination isn't for you. Maybe in centuries, if humans evolve or modify themselves into something that doesn't require oxygen and gravity and social contact, those post-humans might venture to the Kuiper Belt. Maybe AI consciousness uploaded to machines will explore it directly. Maybe our distant descendants will be so different from us that the challenges we face become irrelevant to them. But they won't be us. Not really. We're staying here, on Earth, or perhaps eventually Mars, in environments where we can breathe and walk and see horizons, where missions last months or years instead of decades, where rescue is at least theoretically possible. The Kuiper Belt belongs to our robots, our proxies, our mechanical children we send into darkness to report back what they find. And they're doing that job brilliantly, better than we ever could even if we survived the trip. That's not a limitation. It's a division of labor. Humans do what we do best, asking questions, building tools, analyzing data. Machines do what they do best, surviving in environments that would kill us, operating for decades without complaint, collecting measurements with inhuman precision. Together, we're exploring the solar system, humans and machines in partnership, each contributing what they're suited for. And through that partnership, we're learning things our ancestors couldn't imagine. The Kuiper Belt is being explored right now, just not by people who'll die trying to get there, by machines that were built for exactly this purpose. And that's exactly how it should be. So when someone asks why no human will ever reach the Kuiper Belt alive, the answer isn't about lacking courage or vision or technology. It's about understanding what's actually possible versus what sounds good in science fiction. It's about making rational choices about where to invest resources and risk lives. And the rational choice is clear. We stay home. We build better robots. We study the data they return. We expand our knowledge without expanding the body count. The Kuiper Belt will always be out there, 4 billion miles away, cold, dark, and utterly indifferent to human ambition. We can see it, study it, understand it, but we're not visiting. Not in person, not in our lifetimes or our grandchildren's lifetimes or any timeline where humans remain recognizably human. That's not pessimism, that's just math. And sometimes, math says no. Human exploration has limits. The Kuiper Belt lies beyond them, and no amount of wanting it to be different changes that fundamental fact. The void between here and there is too vast. The timeline too long, the challenges too severe, the human body too fragile, the mission too pointless. That's why no human will ever reach the Kuiper Belt alive, because the universe doesn't care about our dreams of exploration. It just is. And what it is includes distances and timelines and radiation levels that biological organisms can't survive. We can accept that reality and focus on what we can actually do, or we can waste resources chasing impossible goals while neglecting achievable ones. The choice seems obvious. The Kuiper Belt will be explored, just not by us, not in these bodies, not in this lifetime. And honestly, that's fine. Some destinations are better observed from a distance. Some questions are better answered by machines. Some limits are better accepted than challenged. This is one of them.